Okay, so what test will always tell you if a compound is ionic or molecular?
Conductivity test.
Okay, so conductivity test is what we kind of call it for short. What did I call it? What was the other term? It was something conductivity. Started with A. Well, the aqueous conductivity test. Okay, and the reason that we're a little sticky on that is that we are testing the solution, not the compound itself, right? Like I didn't take the conductivity tester and just stick it in the powder, right? I actually dissolved it first. Now, I'd probably let conductivity test go, but just know that it is actually called the aqueous conductivity test. Okay, a substance that dissolves another substance is a solvent. Yep. All right, a mixture with two visible parts.
Heterogeneous mixture.
A heterogeneous mixture, yeah, or a mechanical mixture I would also accept. Okay, names for these compounds. Number 4, ionic or molecular? Okay, so I would write the name of the metal, and then the name of the non-metal. Okay, do I need any prefixes? Do I need any Roman numerals? No. Okay, number 5, ionic or molecular?
Molecular.
Molecular, 2 non-metals. Okay, so what prefix should go on the sulfur? Okay. And on the nitrogen? Okay. For number 6, ionic or molecular? Ionic, lead's a metal, plus we have a polyatomic ion. Okay, so name the metal, lead, what's this stuff called?
Nitrate.
Nitrates. Okay, does that one need a Roman numeral? Which one? 2. Okay, here's why. Nitrate is a -1. There are 2 nitrates for a total of 2 negative charges. I need to get 2 positive charges. I only have 1 lead to get them from. Lead, 2 nitrates. Okay, questions on the naming? All right. Writing the formula, potassium carbonate, ionic or molecular? Ionic. Okay, potassium is a metal. So I write the formula for the metal and its charge. I write the formula for the non-metal, in this case a polyatomic ion, and its charge, and then I drop and swap. 2 goes here, 1 goes there. We don't write ones. You could write it like that, or you could bracket the carbonate as well. Okay, questions on 7? All right, number 8, iron 2 phosphide, ionic or molecular? Ionic. Iron's a metal. Okay, plus we only ever see Roman numerals in an ionic compound. All right, so iron, and what charge do I put on iron? 2, because that's what the Roman numeral tells me to do. And it's with phosphorus, which is a -3. So, drop and swap. Fe3, P2. Okay. All right, disulfur trichloride, ionic or molecular? Okay, so how many sulfurs? Okay, how many chlorines? Okay, what if it was tetrachloride? What would it look like then?
4.
Okay, would I reduce that? No. Why wouldn't I reduce it? It's molecular. I reduce it if it's ionic, right? Okay, so if it's ionic, I reduce. If it's molecular, the prefixes told me it's 2 and 4, it's 2 and 4. Okay? All right, soluble or not? Sodium sulfate. Pretty sure that one's soluble, yeah. Okay, silver chloride. Not soluble. There's very few silver compounds that are. Okay, and potassium hydroxide. Not, oh, soluble. Because there's group 1 ions in the second row, does it not? OH, group 1 ions in the, yeah. Okay, that first row, okay, or sorry, second row down says group 1 ions. Potassium is a group 1 ion. That is soluble. Okay? Everyone follow me on that one? I see a few frowning faces on that one. Okay, does it make sense though? Group 1? Okay. is this what you should expect tomorrow? Yes, except more questions. Okay, this is kind of an abbreviated version of tomorrow's quiz. Yeah, you'll get some stuff on properties of compounds. That was the aqueous conductivity test. Maybe I might ask you, about the colors of some of the metals, or what makes an acid, what makes a base. Okay, then you got some solubility stuff, terminology, right? You could have stuff about precipitates, or solutes and solvents and things like that, terminology. Okay, definitely some of this stuff here. The one thing I forgot to put in this quiz is stuff about the polar nature of water. Okay, polar means electrons. Ooh, I think some people have some reading to do.
Electrons are not equally shared.
They're not equally shared. Okay, if the electrons are not equally shared, one end ends up positive, the other end ends up negative. You can get hydrogen bonding. Okay, when you get hydrogen bonding, you can get cohesion, adhesion, all the stuff we talked about yesterday. Go over the second part of lesson 8 for sure. Okay, there will definitely be some stuff about the polar nature of water on tomorrow's quiz. Okay, and then obviously some naming and writing of formulas. Okay, that's the short version of tomorrow's quiz. Okay, any questions on that? All right. So today we're getting into chemical reactions. It is at this point that you must be able to write formulas and names reliably. Okay, because if you don't, reactions gets really hard. Okay, it's like here, play basketball, but you don't know how to do any of the things in basketball. You don't know how to dribble, you don't know how to shoot, and you don't know any of the rules. Okay, and you're colorblind, so you can't tell who's on your team or not. Okay, like if you can't write names and formulas reliably, you will be literally that, well, crippled. Okay, in terms of being able to do reactions. Okay, so definitely important to be able to write the formulas. Okay, let's quickly review here. If a chemical reaction, chemical change, occurs, how will I know? What are some signs?
Color.
Could be a color change.
Temperature change.
Could be a temperature change.
Odor.
Could get an odor. Okay? An odor is a sign that what's been produced?
Gas.
A gas. What's another sign that a gas is produced?
Vapor.
Okay, that would be the smell. What sometimes do I see when a gas is involved?
Less substance in the beaker.
Okay, there might be a decrease in the volume. Bubbles and fizzing is also another good indication, okay, that a gas has been formed. Only reason I bring that up is when we do our lab, okay, we're going to have some reactions that bubble and fizz, and some reactions that produce a gas, but you won't see a single sign of it. But man, is it going to curl your nose hairs. Okay, there'll be no visible sign that a gas is evolved, but suddenly it'll be like someone took those smelling salts you sometimes see in like the weightlifting, Olympic weightlifting, and they break those things under their nose and the guys go crazy and then they go lift massive amounts of weight. Okay, be like that, all right? So smell, bubbles, color, temperature, what else? Something we talked about yesterday that could form in a reaction if something wasn't soluble. Starts with a P. The precipitate, yeah, could get a precipitate form. All right, so we got temperature changes, okay, all those kind of things, that's good. Those are the signs of a chemical reaction. Why do I see those signs? Why are those the signs of a chemical change? Exactly. A new substance is produced, okay? Same elements, but new substance. Does that new substance have different physical properties than the old one? More than likely. Okay, I mean, we just did a lab that said every compound has different physical properties. So if I have a chemical reaction, okay, I'm going to see some of these signs. Temperature change because the entropy is different. Okay, maybe it's gone from high to low and given off a bunch of energy. Okay, color change, maybe it's just a different color. Okay, solubility, maybe it's a precipitate because something I formed in the reaction isn't soluble anymore. All of those things are the signs of a chemical change because they indicate you made something new. All right? Now, according to Dalton, in a chemical reaction, atoms can be separated, they can be joined, they can be rearranged. All right, so in a reaction like this, okay, does that follow what Dalton says? Right? I didn't really separate or join, but I definitely rearranged, okay? Did I make any new elements? All the same elements, right? It's sodium, sulfur, magnesium, and chlorine on both sides. Didn't make any new elements because Dalton said you can't do that. What rule have I broken? Nope, they can be. It's okay for it. Nothing mechanically about putting the things together is wrong, but I did do something.
Not all of them are there.
Did I miss one?
No, well, they have like twos.
Ah, right. On this side, I have more stuff than I do on that side. Isn't that against the law of conservation of matter? Right? That's the rule that says you cannot create matter and you cannot destroy matter. I have apparently done that. Okay? I've apparently destroyed some atoms here because on this side I clearly have 2 sodium atoms. How many do I have over there? Just 1. Okay, I'm not godlike, so I can't destroy matter. I've done something very wrong. Okay? In a chemical reaction, not only can atoms be separated, joined, or rearranged, but they must be conserved. Okay, that's the law of conservation of matter or mass, whichever way you're taught, it's the same thing. Okay, so on this side, I have 2 sodiums. I need to make sure I have 2 sodiums over here. Can I do this? Most of you are scowling at that, and you're right to scowl at that. No, I can't do that. Is that how sodium and chlorine go together? No. Okay, I can't change what I have. What I can change is how much of it I have. Okay, I haven't changed the sodium chloride. I've just said I got twice as much of it. Okay, in order to, when I do that, or because I do that in order to make sure that I have 2 sodiums on this side and 2 sodiums on this side, 2 chlorines on this side, 2 chlorines on that side, right? I'm saying I have 2 sodium chloride molecules. That means I've got 2 sodium atoms and 2 chlorine atoms. Now, is the reaction okay? Yeah. I've got 1 magnesium on both sides. I've got 1 sulfur on both sides, 2 sodiums, 2 chlorines. Okay? This is what we call a balanced chemical reaction. All chemical reactions have to be balanced because the laws of physics are immutable. Okay? I have to obey that law of conservation of matter, okay? Which means I've got to make sure my equation works out. And I just put numbers in like that called coefficients to make sure. Okay? Was the math of that terribly complex? No, this is not astrophysics. Okay, like you just have to like multiply and divide. Okay. All right, I would like you to write that reaction down because we want to use it to identify the parts of a chemical reaction. Okay, this side here on the left of the arrow, we call those the reactants because they react. So reactants. Okay, this side is what's produced by the reaction, so we call it the products. would this reaction be okay? Okay, is it okay according to Dalton? What did I do with those two elements? Did I join them or combine them in a simple whole number ratio? Okay, that part's okay. What's wrong with it? Is it balanced? It's not, right? There's one potassium on the reactant side. There are how many on the products? 3. That's not good. Okay, I gotta fix that. Plus, I got 2 nitrogens in the reactants and only 1, okay, in the products. So I should probably fix a couple of things. I'm gonna start with the nitrogen, okay? If I put a 2 here, will that make my nitrogen work out? Yeah, and I can do that. I didn't change the compound, I just said I have 2 of them instead of 1. Now, when I do that, how many potassium do I have? 2 times 3 is 6. Okay, what do we need to put here? 6. Now I got 6 on both sides, 2 on both sides. Okay, is reaction balanced now? Okay, that's the extent of the math you have to do, okay, for balancing a chemical reaction, right? I just gotta look around and go, okay, I gotta make sure that I got the same number on both sides, okay, what can I do to make these work? Sometimes you have to find the lowest common multiple. That's kind of what we did, okay? Like 6 was the lowest common multiple here, so we did that, okay? And we made it work. Okay, everybody okay with that one? Okay, so what would these two things be called? These are the reactants, right? Okay, and this single thing would still be the product. Yeah, it's the only one, right? It's just one product. Okay, what about this reaction? Besides the fact it's not balanced, is the rest of it okay? In a chemical reaction, atoms can be separated, joined, or rearranged. Did I separate them?
No.
Yeah.
I had N3P5 as a compound, now I have N and P separated. Yeah, that's okay, that's a chemical reaction. The compound broke down, okay? And now it's into its 2 elements. How did I know what numbers to put beside those ones? I don't expect you to remember, we talked about it like the very first day. Okay, some of the elements on the periodic table are what we call molecular elements. When they're by themselves, they're a molecule, not a single atom, okay? Like sodium is a single atom. When it's by itself, it's just an atom, one single sodium. Whenever you write oxygen, how do you write it? No, I mean like if you're writing oxygen gas, you would write O2. Okay? Why do we write it like that? Because oxygen is one of the molecular elements. Okay? You never see oxygen as single atoms. It's always paired up with itself, O2. Okay? And oxygen is not the only one. Okay? These 3 here, and all the ones down here in group 17, those are also from nitrogen over and then down, those are all 2s. When they're by themselves, they're a 2. Okay? That's how I knew to write a 2 beside the nitrogen in both of these reactions. It's a molecular element. Yes, you will be required to know which elements are molecular. Okay? Hydrogen, also a molecular element. This is a 2. Okay, what did I write beside the phosphorus? 4. Phosphorus is also a molecular element, but it comes as a 4. And the last one is sulfur. Sulfur comes in groups of 8. So when sulfur is by itself, it is S8. Okay? We'll go over that again, but it's important for you to know which ones are which. Okay, so this reaction's okay. I've separated the atoms from each other in that compound. What should I start with to balance this reaction? There's a lot of numbers in this one, right? Here's the answer. When you're balancing a reaction, start with the biggest number. If you can make the biggest number balance, the smaller numbers will generally fall in place. Okay? So what's the biggest number in this reaction? 5. Okay. On this side I have 5 phosphorus atoms. On that side I have 4. How do I make 5 and 4 balance?
Take one out.
Can't take any out.
You put 5 on the left, no, 4 on the left side and 5 on the right side.
Right. I find the lowest common multiple. Okay. Lowest common multiple of 5 and 4 is 20. Okay. So if I put a 4 here, as was suggested, okay, 4 times 5 is 20. What do I need to put in front of this? 5, because 5 times 4 is 20. Are my phosphorus balanced now? I got 20 on both sides, right? What about my nitrogens? How many nitrogens are on the reactant side? 12. 4 times 3 is 12. What do I need to put in front of the N2 to get 12? 6. Reaction's balanced now. 20 phosphorus on both sides, 12 nitrogen on both sides. Okay, that's the extent of the math. Right? Lowest common multiple and make them work out. Okay, start with the biggest number. Okay, let's look at the different reaction types here. I've actually drawn like 3 of them up there already, but let's have a look at what they are called. Okay, we already talked about this. In a chemical reaction, final products are chemically different than the starting reactants. Okay, that's why we get color changes, temperature changes, things like that. We made something new, right? Can you, in a reaction, get the reactants back? Not without like doing a ton of work in some cases. No, you can't in most cases. I mean, you can't unburn a campfire. Okay, that's a chemical reaction. Okay, you got hydrocarbons in the wood, they react with oxygen, they produce carbon dioxide and water vapor. You can't get the firewood back. Right? You can't unburn a fire. There's no way to reverse that reaction. Some reactions are reversible, provided you put the energy back. You use one every single day. Some of you probably more than once a day. What am I thinking of?
Lights?
Nope. But they are they do kind of come from a reaction. Every time you charge your phone, you're making a chemical reaction go backwards. Okay? There's a chemical reaction that allows the energy from the battery to be released. When you plug it in, you make it go backwards. Okay? You get the reactants back. Can you do that indefinitely? No. Most batteries about 1,000 cycles. Okay? After that, they're pretty much cooked. Okay? I don't remember how many times I've charged my phone now, but it's down to like 84% or something on the battery life thing. Okay, it doesn't charge past 80% anymore. Okay, making sense? Okay, so chemical reactions, okay, I take reactants, I get products, I don't get them back, okay, stuff has changed. All right, first chemical reaction type, probably the simplest, okay, we're looking again back at Dalton. Atoms can be separated, they can be joined, they can be rearranged, and if they're joined, they do so in simple whole number ratios. Okay, so that's what's happening in a synthesis reaction. I am joining 2 elements together to form a compound in a simple whole number ratio. Okay, I would definitely have, if you don't have the notes printed or anything like that, this is definitely something you want written down, including the 2 examples that are there on the board. Okay, so in the simplest form of a synthesis reaction, which is what we'll deal with most of the time, two elements combine to form a compound. Synthesis reactions can be two compounds combining to form a larger compound. They can be three compounds combining to form a larger compound. Okay, but we're generally just going to deal with the simplest kind. Two elements combine and make a molecule. Okay. So, in the first reaction there, I have solid magnesium, so probably a strip of metal, okay, reacting with oxygen. So I probably just left it out exposed to the air, right? You leave magnesium out exposed to the air, it will oxidize. It will react with oxygen, and it will produce magnesium oxide. There's kind of a, if you've ever seen what tarnished silver looks like, okay? This is kind of tarnished magnesium. Okay? It's just a black powder. If you rub your fingers on it, it comes off on your fingers. It's just a black powder. Okay? It's an ionic compound, okay? Metal, non-metal. Okay, so that, incidentally, that's what the S and the G, they stand for. This is gas solid. Okay, so solid magnesium reacts with oxygen gas, produces magnesium oxide. Okay, 1-to-1 ratio, is that a whole number? Okay, is that reaction balanced? Okay, how many magnesium on this side? 2. How many over here? 2. Okay, how many oxygen here? Okay, how many over there? What's the difference between this 2 and this 2?
2 is doing the whole equation, 1 is just doing
Kind of, yeah. I get where you're going with that. Okay, this 2 applies to, say, there's 2 molecules of this. This little 2 says in this molecule there are 2 atoms. Okay, so the small 2's indicate bonded together numbers. Okay, the big numbers say there's 2 of this. Okay, there's 2 of this compound or 2 of this molecule hanging out there. All right, the little 2's we use to indicate the structure of something. The big 2's are the amount of something. Okay. And we can use any number. It doesn't have to be a 2. It can be a 3. It can be a 10. Okay, it just depends on what you need to balance that reaction. All right, second reaction. Potassium reacts with bromine to make potassium bromide. Balanced? 2 atoms of potassium, right? 2 atoms, 1 molecule containing 2 atoms gives me 2 molecules. I still have 2 reds and 2 blues. Okay, so it still works out. Okay, everybody all right with that? Okay, so in a synthesis reaction, 2 elements combine to form a compound. It is going to be crucial for you to be able to look at a reaction and tell me that's a synthesis reaction, that's a combustion reaction, that's a replacement reaction. Okay, you got to be able to tell me which one's which just from looking at it. Okay. All right, the opposite of synthesis is decomposition. Okay, synthesis means to put something together. Decomposition means to break it apart. So, a simple decomposition reaction looks like a synthesis reaction in reverse. Okay, we start out with a single compound and it breaks down into its 2 elements. Okay, that's simple decomposition. Decomposition in general means one thing breaks down into many things. Okay, we will come across a few reactions where one large compound breaks down into smaller bits, like 3 smaller bits. Okay, it's still decomposition. So, first reaction there. That reaction is the reaction that Mark Watney nearly blew himself up with in The Martian, okay, where he lost his eyebrows and had his hair all singed. Okay, he was trying to get the hydrazine, okay, to break down into breathable oxygen for himself, okay, and hydrogen gas is a byproduct of that, and he had forgotten just how much oxygen he was exhaling, and there was way more oxygen in the hab than he thought, and it blew up. Okay, he went flying backwards after his triumphant woo, and then he blew up. Okay, so that's the reaction that we actually use to make rocket fuel. Okay, it separates hydrogen from oxygen in water by arcing electricity through it. Okay, you run a high voltage electric current through water and it will separate into hydrogen and oxygen. oxygen. Okay, is that reaction balanced? Okay, how many hydrogens do I have here? 4, right? There are 2 water molecules in every water molecule. There are 2 hydrogen atoms. 2 times 2 is, okay? Here, 2 times 2 is, okay? And on this side, how many oxygens are there? 2. How many over here? 2. Does it matter that it's a molecule now? As long as the atoms are accounted for, that's all that matters. Okay. All right, another decomposition reaction. I've got 2 molecules of nitrogen triiodide. Okay, looking like this. It's breaking down into 1 molecule of nitrogen gas and 3 molecules of iodine liquid. Okay. Again, this is the type of reaction where you have to remember which molecules are, or sorry, which elements are molecular elements, because then you'll know I have to write N as a 2, I as a 2, okay, P as a 4, okay, whatever on the other side. That's where you have to know this. All right, questions on the decomposition reactions? Okay, so we can always recognize a decomposition reaction. It's the only reaction type that starts with only 1 reactant. Okay, only 1 reactant. Okay, your molecular elements. Okay, here they are. All the ones in yellow, those are 2s. Okay, all the ones highlighted in yellow are going to be 2s when they are by themselves. Okay, they could be any number in a compound. When they're by themselves, they're a 2. Okay, and that would include as well, even though it's not colored that way, hydrogen. And that's not yellow. Okay, hydrogen is also a 2. Okay, phosphorus is a 4. Okay, it's in purple. Sulfur is an 8. It's in orange.
Sulfate?
Sulfur's 8. All right, so we've talked about a synthesis reaction where 2 elements combine to form a compound in a simple whole number ratio. We have talked about a decomposition reaction where a compound breaks down into its 2 elements. Okay, the next reaction we're going to talk about is a combustion reaction. What does combustion mean is going on? It could be blowing up, but definitely burning. Okay, anything that's combustion means that there has been a reaction with oxygen, right? All fire requires oxygen in order to burn, all right? So if we have a combustion reaction, we are talking about something burning in the presence of oxygen, or rather, something having a chemical reaction with oxygen. Okay, so combustion reactions, okay? Combustion reactions are generally a hydrocarbon. That is a molecular compound containing carbon and hydrogen. Okay, those are generally our fuels. Okay, reacting with oxygen. Okay, that's going to produce fire, heat, and always the same 2 products. It doesn't matter what you burn. Fire always produces carbon dioxide and water. Okay. It's why on a cold winter day when you're behind somebody at a stoplight, you can sometimes see water dripping out of their tailpipe. okay, usually means that it's cold enough that the water vapor produced when the gasoline is being burned is actually condensing back into liquid water along the length of the exhaust system. Okay, only happens on really cold days. Okay, sometimes if a car isn't running properly, you'll also see water coming out just because it's not running properly. Okay, but water and carbon dioxide are always the two things produced in a combustion reaction. Nothing else. Doesn't matter what hydrocarbon it is. Carbon dioxide and water are always the products. Okay. All right, in this particular reaction, okay, we have, okay, a hydrocarbon, C3H8. Does anyone know what that's commonly called? Okay, it comes in a little white tank, sits beside the barbecue.
Propane.
Propane. C3H8 is propane. Okay, so very common cooking fuel. Burning, obviously, in the presence of oxygen. You see a hydrocarbon, CH, okay, reacting with oxygen. Products are going to be CO2 and water. Now, is that reaction balanced the way it's written? Can we check? Okay, how many carbons here? How many here? 3, right? The 3 means multiply the molecule behind me by 3. Okay, so I got 3 carbons. How many hydrogens do I have?
8.
Okay, how many hydrogens here?
8.
Okay, how many oxygens here? 10. Okay, how many here?
6.
Plus 4 more? 10. Balanced? Looks like it. Okay, so still a balanced chemical reaction. Here's the thing with combustion reactions. Their balancing has different rules. The last 2 reactions, we just said start with the biggest number and everything will work itself out. That works for every reaction type except this. Okay? This has a different set of balancing rules. So, what I want you to put in your notes here are the 2 rules for balancing combustion reactions. Stop doing that. Okay. All right, rule number 1. Balance the reaction in alphabetical order. Incidentally, RXN is shorthand for reaction. Okay, so you see me write RXN, it's me using shorthand. Okay? The reason we balance in alphabetical order is because oxygen is in 3 places in that reaction. And if I try to balance it first, it is a nightmare. Okay? So if we balance in alphabetical order, we make our lives easy. So just going to demonstrate here with this reaction, which you can write right underneath that rule. I'm going to balance that chemical reaction in alphabetical order. What letter am I starting with?
C.
C. Okay? So how many carbons are there on the reactant side? 5. Okay. How many are there over here right now? Just 1. All right. What do I need to put in front of this to make it work?
5.
A 5. Yeah. Okay. Now I'm saying there's 5 carbon dioxide molecules, which gives me 5 carbon atoms on both sides. So I balance the carbon. Right? There's 5 on both sides now. Yeah, I messed some other stuff up. Don't worry, I'll get to it. Okay, by putting that 5 there, I know I made more oxygens as well, but I'll get to it. How many hydrogen here? Okay, how many over here?
2.
Just 2. What needs to go in front of this to make 12? 6. Okay, here's why I balanced in alphabetical order. I have no idea what number to put here when this reaction first starts. But now, I've got numbers in front of both molecules on this side. Can I figure out how many oxygens there are? And I know I have to have the same number over here, right? Okay, how many oxygens here? 10. Plus 6 more? 16. What times 2 gives me 16? 8. Okay, reactions balance. 5 carbons on both sides, 12 hydrogens on both sides, 16 oxygens on both sides. Okay, if I balance it in alphabetical order, it'll always work out. Do I have to do a tiny bit of math? Yep, but not too much. All right, now you're probably thinking, so Coder, you said there's 2 rules. We did just fine with 1 rule. What do we need a second rule for? Okay, here's why we need a second rule. Okay, as we said before, it doesn't matter what hydrocarbon is burning, I always make carbon dioxide and water. If I balance this alphabetically, something's going to happen. Okay, let's figure out what. How many carbons over here? Okay, so what needs to go in front of this? 4. Okay, how many hydrogen here? Okay, what needs to go here? 5. Okay, now 4 times 2 is 8 oxygens, plus 5 more is? 13. What times 2 gives me 13?
6.5.
Right, can I have 0.5 molecules?
No.
No. Okay, there's the problem. That's why we need a second rule. The first rule works as long as you have an odd number of carbon atoms. It doesn't work if you have an even number of carbons, because you'll end up with a decimal in front of one of the molecules, and you can't have that. Okay? You cannot have half of a molecule, or worse, half of an atom. Okay? We know that that's not possible. So, we have the second rule. Okay? Now, second rule is the rule of 2. Okay? If you're a Star Wars fan, you know what I'm referring to when I say the rule of 2, right? It's about the Sith. There are always 2, a master and an apprentice. Well, in the rule of 2, we go like this. Okay? If an even number of carbons have you, start your balancing with a 2, you must. Okay? So, you got an even number of carbons, you put a 2 at the start of the reaction. And then follow rule number 1. Okay? Let's see if this works out now. How many carbons do I have?
8.
Okay, so what do I need to put here? An 8, right? Okay, that gives me 8 carbons. 2 times 4 is 8 carbons. How many hydrogens do I have? 20. Okay, what needs to go in front of this?
20.
What times 2 will give me 20?
10.
10. Okay, 8 times 2 is 16. Plus 10 more is 26. What is 26 divided by 2? Does it work now? Okay, that's why we have the rule of 2. Okay, so the rule of 2 goes like this. Okay? Okay, if you have an even number of carbon atoms in a combustion reaction, you start with a 2, then balance in alphabetical order. Okay, so combustion reactions have 2 funny rules to make them balance. Everything else, biggest number, go from there. Okay, everything else is easy, just biggest number, balance it first. Okay, but for combustion reactions, alphabetical, even number, start with 2. Okay, anybody need that one anymore? All right, I'm gonna give you a little break, say about 5 minutes, and then we're gonna start talking about the replacement reactions. We have 2 reaction types left, but they're very, very similar, so they'll go quickly. So I'm gonna give you 5 minutes, 11:06, we're back at this, okay? So talk amongst yourselves. Okay, so the last 2 reaction types are both replacement reactions. One is a single replacement reaction, and the other is double replacement. They work pretty much the same. Okay? The big thing to remember about replacement reactions is they're always going to involve ionic compounds. Okay? You're never going to see a molecular compound in a replacement reaction. It's always going to be ionic because they're the ones that can split into metal and non-metal, and that's necessary for things to be replaced. Okay? So, the first type of replacement reaction is a single replacement reaction. Right? In a single replacement reaction, okay, you have an element reacting with an ionic compound in the reactants, and then you have in the products, okay, a different element and a different ionic compound. And what has happened is that first element has replaced the part of the ionic compound that it is like. Okay? So in this reaction here, we have as our lone element copper. Okay? Copper is what kind of element?
Metal.
It's a metal. All right? So in this reaction, when it reacts with silver nitrate, it can only replace the part of silver nitrate that is the metal, which would be
Silver.
silver. So what's going to happen is copper is going to replace silver. So copper will go from being alone to being with nitrate, and silver will end up by itself.
Would the 2 stay there still? So it would be 2 copper, or would it be 2 silver?
Well, there's only one copper here, right?
Right.
Okay, copper has a 2+ charge. Silver has a 1+ charge. That's why over here, we've suddenly got brackets around the nitrate and a 2, and why silver is a 2 over here by itself. Okay?
So silver's going to stay at 2, and we're still only going to have 1 copper.
Right, exactly. Yeah, because I can't create or destroy anything. Right? Now, what does this reaction produce?
Copper to nitrate.
And
I don't know what AQ is.
Ag is
Silver.
silver. This reaction produces silver. Silver is valuable. Why aren't we doing this reaction all the time? Okay, seems like a way to get rich, right? As long as I got silver nitrate and copper, I can make silver. Copper's, well, expensive, but not as expensive as silver. Okay. Why doesn't this reaction get anybody rich?
You're starting with silver and just splitting it up.
Yeah, well, and silver nitrate is expensive because, well,
Silver.
let's get silver in. Okay, you can't get rich with that because silver nitrate's expensive to get. Like, we have very small quantities of it. Okay, now this reaction, okay, when you do it, looks pretty cool though. Okay, so let's say, if you guys have seen a penny in your life, right? Like, I know they've been out of circulation for a long time, but okay. So if you take a penny and you drop it into a solution of silver nitrate and come back, like leave it overnight, come back in the morning, the solution will go from being clear to blue, and the penny will be silver. It'll still look just like a penny, but on the surface of the penny will be a layer of plated silver. We call the process electroplating. We actually use it for like corrosion protection, but we plate with like zinc and other sacrificial metals. Okay? So the penny is still there. You can just like scrape the silver off with your thumbnail. Okay? It's just plated out on the penny, but there's a little less copper in that penny now. And that's why the solution is now blue. Okay? That solution now contains copper 2 nitrate. Okay? All copper containing ionic compounds are blue. So overnight you see this solution go from clear to blue, and you see the penny turn silver. Okay? The silver just plates out onto the surface as the 2 metals switch places in that reaction. All right? Now, what if instead of copper, what if I had this reaction instead? What if I had this reaction? So Okay, so I don't start with a metal, I start with a non-metal. What's going to be different?
It's gonna switch with the non-metal
Right.
instead of the metal.
It's going to switch with the non-metal. Okay, so now I'll have bromine by itself, okay, special element, right, comes as a 2, and sodium chloride. Okay? Whatever that lone element is, it replaces the part of the ionic compound that it is like. Okay, so if I have a metal reacting with an ionic compound, the metals will switch places. If I have a non-metal reacting with an ionic compound, the non-metals switch places. Okay, so the analogy they have here is maybe a bit outdated because chemistry is old-fashioned. Okay, but in the example here, you got this guy who represents copper. Okay, this guy who represents silver, and this gal who represents nitrate. Okay, during the reaction, he replaces the other guy. Okay, the guy ends up by himself, and the guy and the girl are together. Okay, and the analogy there is that in an ionic compound, you have to have a metal and a non-metal. Okay, you couldn't end up with like 2 non-metals together. All right, that's chemistry, not real life. I'm not making any commentary on couples and things like that. Saying that in chemistry, that can't happen. An ionic compound is always a metal and a non-metal. Everyone okay with that? Okay, so if this was a non-metal, there'd be a girl here, okay, and she'd replace the other girl, and the other girl would end up by herself, okay? As long as we always get a metal and a non-metal as a pair, okay, and then whatever are replaced by themselves. Okay? Everybody all right with that idea? Okay, is this reaction here balanced? Okay, how many copper here?
1,
Okay, how many copper over here?
1,
1. Okay, how many silver here?
2,
How many silver here? Okay, how many nitrate here?
3.
2. 2. Okay, remember, this could also be written like this, and it often makes more sense to write it like that. How many nitrate are there now?
2.
2, right? What's in brackets is nitrate. This 2 says there are 2 of them. Over here, are there 2 nitrates? Yeah, then that reaction looks balanced to me. Okay, polyatomic ions, they stay together. Their little numbers aren't going to change. Okay. All right, so that's single replacement. Element reacts with ionic compound, makes new element, new ionic compound. Same elements all the way along, but who's with who changes. Now, a double replacement reaction is very similar. It's 2 ionic compounds. Okay? The 2 ionic compounds are going to react with each other, and the metals are just going to switch places with each other. Okay? That's all that happens in a double replacement reaction. Okay? I start out with these 2 ionic compounds, and I end up with 2 different ionic compounds because the metals switch places. Okay? It is very common to get a precipitate in these kind of reactions.
Can I use the bathroom?
You can. Same thing? Oh, yeah, go ahead. I usually have one of each go. All right. Is that reaction balanced? Okay. 1 calcium. 1 calcium. Okay. How many chlorines here?
2.
Okay. How many chlorines over here? 2. How many sodium here?
2.
Okay. How many sodium here? How many carbonates? 1 carbonate. Remember, carbonate is CO3. That's 1 carbonate. Over here, how many carbonates? 1. There's 1 on each side. Okay? Those polyatomic ions are tricky.
Will it ever have like brackets on it?
It could. We could totally have brackets on this. There'd be nothing wrong with that.
Like
Okay.
if it's in a test, it won't come with brackets.
No. I don't usually put brackets around them if they don't need it. Okay? It's not wrong to do it. I just don't usually. You can totally just write on the test, put brackets around it if you want. Totally fine. Okay, so double replacement reactions are always 2 ionic compounds, and all that happens is switch the metals, you got your new ionic compounds. Okay, you got a different metal-non-metal combination on the other side. Okay? All right, questions there? Okay. Remember, this stuff is not on tomorrow's quiz, okay? So if you're looking at this stuff and going, oh my God, I feel like I'm drinking from a fire hose, it's okay. We're gonna be working on this for a long time, okay? Reactions are like the biggest thing in this whole unit. Okay, when we're writing chemical reactions, one of the most important things is to make sure that we have obeyed Dalton's rule, okay, we haven't created any new elements, okay, and the law of conservation of mass, that we haven't made more or less of anything in the reaction, okay? Now, this reaction is a tricky balance because oxygen is in every single compound in that reaction. Okay? This is not one of the reaction types we went over. Okay? I'm just showing you, here's what can happen. Sometimes balancing can get pretty tricky. Okay? So how many nitrogen right here?
3.
3. Okay. How many nitrogen on this side?
3.
2 here, plus
1 there.
1 more is 3. That's what you have to remember. This plus sign isn't just saying this and that. It's also saying add the numbers together. We only care if it's like a scale and the arrow is the pivot point, that there's the same amount on both sides. It doesn't all have to be in one compound. Okay? All right, how many hydrogen here? 2. Okay, how many hydrogen on this side? 2. All right, oxygens, how many here?
6.
6.
Plus?
1.
Okay, so we got
7.
7. 2 times 3 is 6, plus 1 is? All right, that reaction's actually balanced. Okay, but it's tricky. Okay, you got to make sure you account for everything. Okay, we're going to work on balancing, guys. Don't worry about it too much. Okay, here's what I want you to do. I want you guys to write these reactions down, these 3 reactions, and tell me what type they are. Write them out in words, so basically write their names, okay? And balance them. All right, give you a few minutes to give those 3 a try. Okay, so in the first one, I have 2 elements, nitrogen and hydrogen, combining to form a single compound. What kind of reaction is that? It's a synthesis reaction, right? So we just write synthesis beside it. Okay, and then I would write it out in words. Okay, N2 is nitrogen. That's how nitrogen comes as an element. Okay, hydrogen, same thing. That's how hydrogen comes as an element. I missed a note. Hydrogen. Okay, is going to make, is this molecular or ionic? It's molecular. They're both nonmetals. Hydrogen is listed second, so this is going to be nitrogen trihydride. Okay, so I've identified the type. I've written it in words. Now I need to balance it. What should I start with?
N.
Biggest, eventually. Okay, biggest number. Okay, everything except combustion, I start with the biggest number. Combustion has its own rules, alphabetical and a rule of 2. Okay, but every other reaction, start with the biggest number. That will literally work 95+% of the time. Okay, there's going to be the odd reaction where it won't work and you'll have to start with something else. Okay, so in this reaction, the biggest number is 3. Okay, I have 3 hydrogens in the products. I only have 2 in the reactants. What's the lowest common multiple? 6. Okay, what do I need to put in front of this?
7.
3.
A 3. 3 times 2 is 6. What needs to go in front of this?
2.
2 times 3 is 6. Did I just fix my nitrogens?
Yeah.
Always a good sign. Okay? Always a sign you've done something right. If a number you wrote fixed something else. Okay? Is that reaction balanced now?
Yes.
2 nitrogens on both sides, 6 hydrogens on both sides. Yep, that's good now. Okay? That's all there is to it. How many people have done the second? Okay, I'm going to give you a little bit more time on the second one, and then we'll look at it together.